Have you ever seen two wires in a power grid gently move towards or away from each other? It might look like magic, but it's pure physics in action. Welcome to the world where moving charges create invisible forces. When two parallel wires carry current, they don't just sit quietly. Each wire creates a magnetic field that reaches out and interacts with the other wire. Now here's the exciting part. If both wires carry current in the same direction, they attract each other. But reverse the current in one, and they repel. This push and pull is governed by the magnetic fields produced by these currents. According to the Lorentz force law, F equals I into L cross B, a wire carrying current I placed in magnetic field B feels a magnetic force. As you'll see in the diagram, these forces arise due to circular magnetic fields looping around each wire. It's a dance of fields and forces.
Let's rewind and first understand, how does a wire create a magnetic field in the first place? Imagine a long straight wire carrying a steady current I. The magnetic field it produces surrounds the wire like invisible circular rings. Using the Biot-Savart law, we can calculate the magnitude of this field at a distance r from the wire. The formula is B equals mu naught, times I divided by 2 pi r. Here, mu naught is the permeability of free space. To find the direction of this field, simply use your right hand, point your thumb in the direction of current, and your fingers curl along the direction of magnetic field lines. This field becomes the cause of force on any nearby conductor.
Now let's get mathematical and derive the force between two long parallel wires. Imagine wire 1 carrying current I. It produces a magnetic field at the location of wire 2, which lies a distance d away. That field is B equals mu naught I divided by 2 pi d. Wire 2, carrying current I, sits in this field. So it experiences a force. According to the Lorentz force formula, F equals I times L times B. Substituting B, we get F equals mu naught I divided by 2 pi d. And that's the key result, a beautifully symmetrical formula showing how the magnetic force depends on both currents and the distance between wires. Interestingly, wire 1 also feels an equal and opposite force, Newton's third law in full swing. Here comes a fun twist. What happens when the direction of currents change? If both wires carry current in the same direction, their magnetic fields align in such a way that they pull each other closer. That's attraction. But if the currents run in opposite directions, the fields now oppose each other and the wires push away. That's repulsion. This behavior is completely consistent with the right-hand rule and visual patterns of magnetic field lines. And don't forget, these forces act perpendicular to the wires in the plane that contains both. You'll see in the upcoming diagram how these force vectors play out in real setups. Now let's connect this concept to something really fundamental, the definition of current itself. The C unit of current, the ampere, is defined using this very interaction. Here's the formal definition. 1 ampere is the current which, when maintained in each of two infinitely long parallel conductors placed 1 meter apart in vacuum, produces a force of 2 times 10 to the power minus 7 newtons per meter. This isn't just academic. It provides a measurable, electromagnetic basis for defining electric current based not on charge flow, but on magnetic interaction. It's one of those rare cases where electromagnetism becomes the foundation of a unit in the C system. Alright, let's put our understanding to the test with an advanced numerical example. Imagine two long, parallel wires placed just 2 centimeters apart, each carrying a current of 50 amperes in the same direction. The question is, what is the force per unit length between them? We start with the formula. Force per unit length equals mu naught times I1 times I2 divided by 2 pi d. Now let's substitute the values. Mu naught is 4 pi times 10 to the power of minus 7. Both currents, I1 and I2, are 50 amperes. And the separation, d, is 0.02 meters. That gives us force per unit length equals 4 pi times 10 to the power minus 7 multiplied by 2500 divided by 2 pi times 0.02. Simplify it step by step. The pi terms cancel out neatly. So we are left with 10 to the power minus 7 multiplied by 2500 divided by 0.02. And that comes out to 1.25 times 10 to the power minus 3 newtons per meter. So, what does this mean? It means the wires attract each other with a force of 1.25 millinewtons for every meter of their length. And yes, that's a measurable effect of magnetic interaction between currents. Let's take a moment to summarize what we've explored today. We began with the fascinating idea that moving charges, electric currents, create magnetic fields. These fields, in turn, exert forces on nearby currents. We derived the formula for magnetic force between two parallel wires and found that the force depends on current strength and distance. Then we saw how the direction of current decides whether the force is attractive or repulsive. And finally, we learned how this interaction led to the precise definition of the ampere, grounding current in mechanical force. I hope this journey helped you see the elegance and symmetry of electromagnetic forces. These principles power motors, define units, and explain the behavior of current-carrying conductors across technologies. See you in the next session, where we'll dive into even more magnetic marvels of physics.